Okay, in this video we're going to describe an application of second-order differential equations to the motion of a particle under the influence of a central force. So let's look first at the definition of a central force, maybe an example of a central force, and then we'll carefully state the problem. So, definition: a central force is a force whose magnitude only depends on the distance from the origin. So I'll denote the origin by a 0 with an arrow over it. So in other words, the distance between a point and the origin, so this is the only determination in the force exerted on an object at point P by the central force. Great. So a very obvious example of a central force would be a gravitational force. And it's well known that gravitational force is proportional to 1 over r squared, where r squared is the distance from the center of that object. And we can put the center of that object at the origin. So, now that we have a definition of a central force, maybe one example which we'll explore in a later video, let's look at the problem. So the problem is to determine the curve traveled by an object whose initial velocity and position vectors are not parallel under the influence of a central force. So I've left a little gap here, and let's see why we need this assumption that they're not parallel. So we make this assumption that they're not parallel because that means they define a plane, and then we can orient our coordinate system so that plane is the xy plane. Which gives us a nice set of coordinates to work in. We only need to work in 2-dimensional coordinates instead of 3-dimensional coordinates. And then finally, the curve that is defined by the travel of this object is called its orbit. So this curve is called an orbit. Great. So this is all our setup. Definition of a central force, a force that only depends on the distance from the origin. Gravitational force is an obvious example of this. And our problem is to determine the curve traveled by an object under the influence of this central force. In other words, determine the orbit. So I'll clean up the board and then we'll get to the next step. Okay, so after we have our basic definitions and the setup of the problem, we can move towards solving the problem. So in polar coordinates, we can represent the central force by the following function. So we can represent it by the vector f r theta equals little f of r, which only depends on the distance from the origin, times cosine theta in the I direction plus sine theta in the j direction. And so notice that gives us a translation between polar coordinates and rectangular coordinates, which will be useful as we set this up. And then let's also notice the following, that the magnitude of the force as a whole is equal to the magnitude of the little f function, which only depends on r. In other words, the distance from the origin. And that's because this is a unit vector. This cosine I plus sine j is a unit vector, which is easy to check via linear algebra. Now, the next thing that we'll do is work towards finding the orbit of an object under this force. And how we'll do that is the following. So let's suppose at time t, the object's position is given in polar coordinates by the following. So we need a tuple in polar coordinates, a distance from the origin, r, and then an angle theta, and those are both going to depend on t. So it'll be r of t, theta of t. So that's the position at time t. Great. And then in rectangular coordinates, that position is given by the following. So that is r of t cosine theta of t in the I direction plus r of t sine theta of t in the j direction. Okay, great. Now we want to set some notation which will simplify some of the calculations. And so we'll set the following. So now we set E1 of t to be equal to, so this will be equal to cosine theta of t in the I direction plus sine theta of t in the j direction. Good. And then we're going to set E2 of t to be equal to the following. So we're going to let that be equal to negative sine theta of t in the I direction plus cosine theta of t in the j direction. Okay, actually, sorry, I'm going to erase this minus sign and I'll put the minus sign right here. Great. And now notice that gives us the following observation. So now notice if we differentiate E1 with respect to theta, so if we take the derivative of E1 with respect to theta, we get negative E2. Great. And then furthermore, by the chain rule, if we differentiate E1 with respect to t, we'll get negative E2 times the derivative of theta with respect to t. So d theta dt times E2, and that's all negative. Okay, so that's all our setup. These E1 and E2 functions or unit vectors that depend on t and theta will be useful as we move forward. Okay, great. So I'll clean up the board and then we'll get on to the next step. Okay, so as to summarize what we had on the previous boards, so we had this force is given by a function f times this vector cosine theta I plus sine theta j. And then next we define these functions E1 and E2 to be used with the position function. So this theta of t is the angle of the position at time t. So notice we have E1 of t is cosine theta I plus sine theta j. E2t is minus sine theta I plus cosine theta j. So there was a slight typo on the bottom of this board previously, but here I have fixed it. And here we have E1 prime, and by prime we mean the derivative with respect to t. So using the chain rule, you can check very quickly that this is equal to theta prime times E2. and then E2 prime is equal to negative theta prime times E1. And remember, theta is a function of t. It is the angle at which the particle is at time t. And then finally, we were able to write the position of this function as r, so that's the distance from the origin, times this function e1 of t, in other words, with this cosine and sine. Okay, great. So the next thing that we want to do is the following, and that is to calculate the force on the particle two different ways. So the two different ways we want to calculate the force on the particle, one by looking at F equals ma given its position, and the other given by the fact that the only force on the particle is what we're assuming is this central force. So in other words, we will have the mass of the particle times the acceleration of the particle will be equal to the force that this central force is exerting on it. And since we know the position of the particle is this r of t, e1 of t, we can calculate this very easily. So we know that acceleration is the second derivative of position. So this is given by r of t e1 of t double prime equals this f of r. Okay, great. So now what we need to do is take the second derivative and see what we get, and we'll use some simplification along the way. So first, let's go ahead and take the first derivative of this, along the road to taking the second derivative. So I'm going to leave out the dependence on t, but the dependence on t is there. So here we'll write r e1 prime. So we need to use the product rule here. So this is going to give us r prime e1 plus r e1 prime. Okay, good. But we know by our setup with the definition of e1 and e2 that we get e1 prime is theta prime e2. So this gives us r prime e1 plus r times theta prime e2. Okay, great. And now similarly, we can take the second derivative. So if we take r e1 double prime, so that's going to give us r double prime e1 plus r prime e1 prime plus, and now we have three functions to take the derivative of, so we can use the product rule kind of three times. So here we have r prime theta prime e2 plus r theta double prime e2 plus r theta prime e2 prime. Okay, great. And now we can continue on this, and we will substitute e1 prime for theta prime e2, and we'll substitute e2 prime for negative theta prime e1. And after all is said and done, so that simplification is like quite elementary, we would get the following. So we'll get r double prime minus r times theta prime squared in the e1 direction. Good. And then plus r theta double prime plus 2r prime theta prime in the e2 direction. Okay, so that's what we get for this second derivative. So now we'll plug that into this mass times acceleration equals central force equation, and then go from there. So I'll clean up the board, and then we'll pick up from that point. Okay, so now we're ready to pick up where we left off. So we have this left-hand side of the equation, which recall we got this left-hand side of the equation by looking at F equals ma, where a is the acceleration of the particle, and this is given by m times the position of the particle, its second derivative. And so we calculated this out carefully given our assumptions of the position of the particle. And then we have the right-hand side of this equation is this little function f of r times E1. And now notice that's equal to capital F of r. Remember, E1 was this cosine theta plus cosine theta I plus sine theta j, and so that wrapped up all that. So that's the central force. So in other words, we're measuring the force on the particle in two different ways by taking its acceleration, in other words, the second derivative of its position, and by looking at the central force. Great. And so now we can see that we have this vector equation, and E1 and E2 are linearly independent. So I won't check that, but that's an elementary thing to check from linear algebra. So that means we can equate the coefficients of E1 on each side of the equation and the coefficients of E2 on each side of the equation. So notice there are coefficients of E1 on each side of the equation, but there's only a coefficient of E2 on the right-hand side of the equation. So let's see. That gives us, so let's see, from the coefficients of E1, we get the following equation. So we get the mass times the second derivative of r minus r, and then theta prime squared. And then on the right-hand side, we get this little function f of r. Okay, great. And then by equating the coefficients of E2, we see that we get the mass times r theta double prime plus 2 r prime theta prime equals 0. Okay, great. So now we can use this fact that we have an equation equals 0 on the right-hand side to have some simplification. So we'll do this as follows. So first of all, we can divide out an m. And we can do that because we're assuming that the mass of the object is not 0. So I should have said that earlier, but we're assuming the mass of the object is not 0. And the next thing that we want to do is multiply by r, and that's going to give us the following equation. So that'll give us r squared theta double prime plus 2r r prime theta prime equals 0. Okay, great. But now, if you look at this very closely, this is actually the derivative of a single function. And that single function is the product of two functions. So now we're going to notice that this is the derivative of r squared times theta prime. So r squared times theta prime equals 0. So notice, if we take the derivative of r squared theta prime, using the product rule, we get r squared times theta double prime, and then we get 2r r prime theta prime. And so that's how we have seen that. Great, but now if we have the derivative of this equals 0, this means that r squared theta prime equals a constant, and so this tells us we can write r squared theta prime equals to h, a constant. And so you might say, well, which constant should we take it to be? Well, we actually have like a very good choice, because this means this is a constant for all values of t. So we are probably given some initial conditions in this setup, so we can just set h equal to r squared evaluated at 0 and theta prime evaluated at 0, and that's our value of h. Okay. Good. So now that we have this set up, we'll move on to this, but I'll clean up the board because we'll need more room to look at this left-hand side of the equation. Okay, so let's recall where we left off. So we left off with needing to make sense of this differential equation where we have r double prime minus r times theta prime squared all times m equals f of r, where this f of r function is related to our central force. And then we also determined that r squared times theta prime is equal to h, which was a constant. So now we want to move on to the following. So let's set u equal to 1 over r, so we're doing a slight change of variables. And so notice that kind of obviously means that u squared equals 1 over r squared. Okay, good. But now, using the fact that r squared times theta prime equals h, which is a constant, we can rewrite this as theta prime over h. Okay, good. But now we can take the derivative of r. So if u is 1 over r, then r is 1 over u. And so we can take r prime, and that's equal to minus u prime over u squared. But we can easily write that as follows. So we know u squared is 1 over r squared. So we can write this as minus h times u prime over theta prime. Okay, good. But now, notice u prime over theta prime can be given by minus h times du dt over d theta dt. But then by the chain rule, that's equal to minus h times du d theta. So let's see here, we have r prime equals minus h times du d theta. But now we can go ahead and calculate r double prime similarly, because look, we're going to need r double prime in our differential equation up there. And we can calculate that. Notice that will be minus h times the derivative with respect to t of du d theta. Okay, so now notice that's minus h du d squared u d theta squared. In other words, the second derivative of u with respect to theta times theta prime, where theta prime is equal to the derivative with respect to t of theta. And so now what we can do, so now we can replace this theta prime with h over r squared, and so that's going to give us the following, minus h squared over r squared, the second derivative with respect to theta, but now notice that is minus h squared u squared, and then the second derivative of u with respect to theta. Okay, good. So that's r double prime, and now we can move to plugging all of this into our differential equation. Okay, so now that we've done the simplifying calculation with r prime and r double prime to put them as functions of theta, we can put this all into our differential equation up here. So what we'll do is we will replace r double prime with this. Let's factor a minus sign out at the same time. So that will give us minus m, and then we have h squared u squared times the second derivative of u with respect to theta squared. Okay, good. And now we have this minus r, and so instead of r, we'll write this as 1 over u. Good. And then, sorry, this should be a plus because we factored a minus out. And now we have theta prime. So now notice that this tells us that theta prime equals h over r squared, which equals h times u squared. So now we're going to square that, we'll get the following. So this will give us h squared u to the fourth, and now we have that is equal to f, and then instead of r, we'll write 1 over u, because u is 1 over r, so r is 1 over u. Okay, great. So now we're all ready to get to the next step. So let's see what we get. So from here, we can divide out by a minus m times h squared u squared, and that's going to give us the following. So that'll give us the second derivative of u with respect to theta plus u equals minus 1 over m h squared u squared times f of 1 over u. So now notice we have like a second order differential equation. It's a linear second order differential equation with constant coefficients. We have a non-zero forcing function though, so this is a non-homogeneous differential equation. So now the summary of this is as follows. So an object with mass m has an orbit under a central force given by r, where u equals 1 over r satisfies this differential equation, which I'll call 1. Okay, good. So that's the end of the video. Now we'll have our next video looking at an example of this.